Okay, so this is lecture 5.3, unit 5, topic 3, and it's about spectroscopy, which is what we can do with the measured values that we can find about wavelength or frequency from radiation that's either absorbed or emitted by substances. And unfortunately, this is a topic that's not very much in your book. So the learning targets for this are largely setting up an outline. There's only one thing here on page 384 that you would need to actually do before you watch this video. So go ahead and get this set up so that you have space and you're not stopping it too many times to write in the middle. And then go ahead and restart the video. Now that you have your introduction, we'll see if we can do this together. So what I want to do with this actually is talk about, instead of talking about it myself, we're going to use the AP Daily video. I really like what they do here and the way they talk about it, especially because this is something that there could be so much more information about, but we want to focus on what College Board thinks you should know and what you should be able to do with it. So the three regions of the electromagnetic spectrum that are addressed in this video would be microwave and infrared and either ultraviolet or visible. So I'm going to see if I can play this video for you, and we'll watch and see what happens here. Hopefully it will cooperate.
Chemistry, topic 3.11, spectroscopy and the electromagnetic spectrum. In this video, we will be talking about the relationship between regions of the electromagnetic spectrum and the types of molecular or electronic transitions associated with those regions. My name is Jordan Rose, and I teach at Free State High School in Lawrence, Kansas. I'm excited to be here with you today. Spectroscopy is the study of matter's interactions with electromagnetic radiation. Matter can absorb or emit radiation in different regions of the spectrum, and those regions are associated with molecular motion or electronic transitions. Microwave radiation specifically is associated with transitions in molecular rotational levels. Infrared radiation is associated with transitions in molecular vibrational levels. Vibrational states of bonds require more energy than molecular rotations. Infrared has a higher energy per photon than microwave, therefore a higher frequency and shorter wavelengths than microwave. Ultraviolet or visible radiation is associated, ultraviolet and visible radiation are associated with transitions in electronic energy levels.
So you should definitely know these three, that microwave radiation is associated with molecular rotation. I think microwave radiation, MR, molecular rotation, MR. You should know that infrared is associated with vibration. So I want to picture IR, vibrate, I don't know, something like that. And that ultraviolet is electron transitions between energy levels. So, and visible as well. So these you should know. Make sure that you have that as a part of the knowledge that you're building.
Electrons being promoted. Here's an example of the electromagnetic spectrum. And in this, you can see that we have microwaves at a very long wavelength compared to our ultraviolet line. We see that our microwaves have a lower energy and a lower frequency as well. Infrared is kind of in the middle of those two. And when we move over to the visible and ultraviolet, we see at that point we have shorter wavelengths as well as a higher frequency and higher energy as well. Let's look at an example together. The diagram above represents the absorption spectrum for a pure molecular substance. Which of the following correctly indicates the type of transition observed for the substance in each of the regions of the spectrum? And so in this example, we have three different regions, X, Y, and Z, and we see that we are getting absorption data for each one of those.
This is largely a memorization type of information question. So notice that we have the ultraviolet and visible region here with some mostly in the ultraviolet, and then we have some in the infrared, and we have some in the microwave. So remember how you can tell them apart. Microwave radiation, so this is showing molecular rotation, and infrared radiation, this is showing molecular vibration. And ultraviolet and visible is what we already knew. So this is electron transitions from higher energy levels to lower, or when it's absorbing like this, from lower energy levels to higher energy levels. So this is largely a memorization type question.
So our multiple choice answers are going to give us some different areas. It's going to look at each of the different regions, and it's going to associate each region with a specific type of motion. So as we just mentioned a second ago, we want to notice that both UV radiation and visible light are going to involve electron promotions. And we also want to make sure that we noticed that we had our microwave wavelengths were going to be our molecular molecular rotations, and the infrared is going to be our molecular vibrations. So if I go through and go look back at my spectrum here, and then I compare that to my answer choices, I notice that region X with the electronic transition matching my ultraviolet and visible. I notice that I have region Y with my molecular vibration, which is going to match my infrared, and my region Z, which is going to match my microwave with the molecular rotation. So my best answer choice here is going to be D. Let's do a practice problem.
This is kind of a complicated question, so I'm going to let her talk you through it, but definitely be ready to ask questions if you have them.
Molecules absorb ultraviolet light, but not visible light. I2 molecules absorb both visible and ultraviolet light. Explain these observations. Go ahead and stop the video here and try this problem on your own. So as we mentioned a minute ago, both types of these are going to involve electron promotions. The UV radiation is going to be more energetic than the visible light. And since the I2 can absorb visible light, there are low-level transitions in I2 that don't exist in the N2. So when we're looking at answering this question, we need to make sure we talk about both N2 and I2. We want to compare and contrast both of those and kind of explain why these observations are happening. So we'll say something about visible light does not produce those transitions between electronic energy levels in the N2 molecule, but does in the I2 molecule. Both the visible and ultraviolet can promote electrons to higher energy levels. Ultraviolet light is more energetic than invisible light, so there must be some lower energy electron transitions available in those I2 molecules that aren't present in N2. And we actually know this because we can actually use the visible light as a tool for differentiating I2 from N2. And this is exhibited by the fact that iodine vapor has a deep purple color, whereas nitrogen gas is colorless.
So that gives you the main idea about the differences between these three types of spectroscopy that you see here, microwave radiation spectroscopy, or infrared, or UV visible. Now I want to look at PES, or photoemission, or photoelectron. You can say it either way, spectroscopy. So let's look at this. Basically, this is a way that is really important. Actually, this is most important right now in this unit because it helps us to understand what we see about electron configurations in the Aufbau order. It's the reason that it confirms what we thought in theory of the Aufbau order of filling in of orbitals from 1s to 2s to 3s, etc., 2p to 3s, like that. And it also helps us understand the reasons for the periodic trends, which are the second part of this unit. So this is a really important foundational piece of information, and it's actually experimental evidence that supports the things that we see in behavior patterns in atoms and molecules. So keep in mind, she's going to refer to Coulomb's law, and this is review, that the force of attraction, so picture the attractions that we're talking about here are the attraction between the positive nucleus and the negative electrons. That force of attraction is equal to the charge. So the more protons you have in the nucleus versus mainly valence electrons here, or that single certain electron, etc., and is inversely proportional to the distance between those two charges. So let's go ahead. I want to watch the other AP Daily video that goes with this, and we'll watch it together. Hopefully, let's be patient for a second. If this doesn't work, I'm going to have you watch it on your own on AP Classroom.
This video is on topic 1.6, photoelectron spectroscopy. Today we're going to cover how to read a PES spectrum.
I think we have buffering going on.
To determine the identity of an element, the electron configuration, and predict the relative energies of the electrons. My name is Alice Cootie, and I'm happy to be back with you on AP Daily. When we think of the atom, we think of electrons as existing in shells and subshells, or energy levels and sublevels, where the inner electrons are the core electrons and the outer electrons are valence electrons. So what you see here is a sample electron configuration where the 1 here would represent the shell or energy level, and the P would represent the subshell or sublevel. But how do we know what order the electrons fill and how many electrons go in each level or sublevel? And so that brings us to Aufbau principle. The Aufbau means to build up, and it is German. And what it says is that electrons will fill lower energy levels first and then fill higher ones later. So if we start at the bottom of the model here, there would be 2 electrons in the 1s, then 2 electrons in the 2s, then 2p. And so we would go from the bottom to the top and then from left to right. But how do we know what this order is and how many electrons go in each spot? And so that brings us to photoelectron spectroscopy, which is also known as PES. And so what PES is a technique that's used to determine the relative energies of electrons in either atoms or ions. And this technique uses high energy radiation to remove an electron from an atom. We already know that electrons are located in different energy levels or subshells, and that valence electrons are easier to remove since they're less attracted to the nucleus, and core electrons are harder to remove because they're more attracted to the nucleus. All right, so let's take a look at an example of a PES. So this example of a spectra here, you can see on the x-axis we have the binding energy, which is measured in megajoules, and on the y-axis is the relative number of electrons. And so the placement on the x-axis indicates how much energy is required to remove that electron from a subshell, and the height of the peaks that you see here is proportional to the number of electrons that are in that subshell. Generally, when we read our PES, we think about the nucleus as being here on the far left, which means that this peak represents the electrons that are closest to the nucleus, and then this one would represent the electrons that are furthest away. When we analyze the peaks here, you should notice that these 3 peaks are the exact same size, which indicates that it's the same number of electrons. And then this larger peak here is about 3 times greater, which indicates there are 3 times as many electrons. So if we take a look at the electron configuration then, again, this peak represents the electrons that are closest to the nucleus, so this would be 1s, and there are 2 electrons there. Next comes 2s2, and again, same number of peaks, same height of peak, which means same number of electrons, and then 2p6. And again, this one has 3 times as many electrons as this peak, and then the last one is going to be 3s2. From here then, we can identify what the element is one of 2 ways. We can either count the superscripts, so 2, 4, 10, 12, and element 12 is magnesium, or we could note that the configuration that ends in 3s2 is for magnesium. We can also use PES to compare different elements. So for example, we're going to take a look at beryllium and magnesium, which we just looked at, and tie this back to Coulomb's law, which was part of the last video. And so I've already filled in the electron configurations for both of our elements, and we're just going to look at the valence electrons in each of these cases. So you can see that for beryllium, its valence electron peak is at 0.90, and for magnesium, it's at 0.74, indicating for magnesium that it takes less energy to remove the valence electron than it does for beryllium. So tying this back to Coulomb's law, remember again, if our R value is increasing, meaning the distance between the electrons and the nucleus is greater, that means the force of attraction is less, and that means that there would be less binding energy. This is the end of the video. Thank you for watching.
So something else that we'll really look at together in class is, if I can get this to drag back, I don't know if it will let me, but something else that we're going to look at together.
Please join me for the next video where we take a look at PES.
Drag her back here. I don't know if it will come in. It's not cooperating. So we'll look at it together once we get back to class.
Remember again, if our R value is increasing, meaning the distance between the electrons.
Sorry for the technical difficulties here. So what I do want you to notice also is that in beryllium, the amount of energy of the binding energy for the 1s electrons is 10 megajoules per mole of electrons. And in magnesium, those same two electrons have a much higher binding energy. So the 1s electrons in magnesium are much more attracted to the nucleus in magnesium than the 1s electrons in beryllium are attracted to its nucleus. This comes back to Coulomb's law again, where you can see that magnesium would have 12 protons. So the charge of the protons here pulling on those same two electrons is much greater in magnesium, meaning the force of attraction for those two electrons, those same two electrons in magnesium, is much stronger. Hence, it takes much more energy to remove those same 1s electrons from magnesium as it would from beryllium. So you kind of want to really keep in mind that this is definitely confirmation for us that those electrons closer to the nucleus are more attracted to the nucleus as we add protons to the nucleus. So we've got lots of things that we can do with this, and we will definitely come back in class and work with PES spectrum data so that we can spectroscopy data so that we can really analyze how it fits together with electron configurations and with periodic trends. So thank you for watching, and make sure you come ready with questions to class.